Hi everyone, this is Dr. Hopkins with our next video in our series for the first semester chemistry class. And today we're going to talk about basic atomic structure and basically what we can read off of the periodic table. So here is an example of the periodic table, or one. You can look up many of them online. This one happens to have the names of the elements in each of the boxes, but just shows you, this is from IUPAC. And so basic atomic structure, atoms basically have a small central nucleus, and we're going to draw this here. So we're going to put a nucleus here, and that's where all the matter is, or almost all the matter is, and it's composed of protons and neutrons. So protons are positively charged, neutrons are neutral subatomic particles, okay, and so those are all packed in that space. And then there's a lot of open space. Now I'm kind of drawing this out. Is mostly empty space with a few electrons, which are the negatively charged particles, out surrounding the nucleus, okay? So most of the mass in the nucleus, and the rest of it is empty space except for a few electrons here and there. And the electrons are very small particles. And so just to show what our subatomic particles are, so the neutron has a charge of 0. Now, when we talk about charge, electronic charge of 0, we're talking about 0 times the electric charge, or the electronic charge. So the charge of an electron is 1.602 times 10 to the minus 19 coulombs. Neutron has 0 charge. Its mass is 1 atomic mass unit. If we were to convert atomic mass units to actual mass units, it would be 1 atomic mass unit is about 1.67 times 10 to the minus 24 grams. Okay? And so that's the mass of the neutron. Like I said, that's in the nucleus. The proton is positively charged, so it's plus 1. So each proton has plus 1.602 times 10 to the minus 19 coulombs. It's easier just to say a plus 1 charge. And the mass is approximately the same. The neutron's slightly larger than a proton, but they're about 1. Okay, so 1.67 times 10 to the minus 24. And then we have the electron, which is out in the other space, and that's negative 1, so negative the charge of the electron. And the mass is approximately 0. It's not exactly 0, but to the significant digits I've written, it's very small. And actually we show it here. It's about 3 orders of magnitude smaller than the mass of a proton and a neutron. So that means that all the electrons out in space really aren't contributing much to the total mass of the electron or the atom at all. And so basically the charge of an atom, so if it's an ion or if it's neutral, comes from the total of the protons and electrons. The charge of the nucleus is the sum of the protons, because remember the neutrons are there, but they don't add any charge, they just add mass. And so the mass of an atom is the sum of the protons and neutrons. Okay, so those are some properties of atoms based on the content of the subatomic particles. So we look at the periodic table here. Each element is in a box. And then the first is the top number. Sometimes it's the top left. Is Z, or the atomic number, and it's the sum of the protons of the element. And the sum of the protons gives us identity. So every element that has 2 protons, only 2 protons, is helium, okay, which is shown in the symbol, which also shows element identity, and in this case it's helium. I didn't write in my box here. Some of the periodic table I showed earlier has the name right underneath the symbol, but most of the time we just write the symbol. You can always look up the name somewhere else. So both these two, both atomic number and the symbol, give identity information about the element or the atom. And then last information is the atomic mass. There's other information that some periodic tables have, but you'll have these 3 components in every one of them. So the atomic mass. Now the atomic mass, 4.0026, is not exactly the sum of all the neutrons and protons, okay? It's the weighted average of all isotopic masses in AMU. And actually we'll get to this grams per mole in a minute. And so I need to define what an isotope is, or an isotopic mass. So if we have two atoms, the same element, but they have different masses. Okay, so if they're the same element, that means they must have the same number of protons, because protons, or number of protons, is an identifying information. And so if they have the same mass, they're isotopes. That means they differ in the number of neutrons. And naturally occurring, there may be multiple isotopes that occur. So what you get is this, what we put in the periodic table was a weighted average based on, their probability of finding that particular component and so forth. So it gives you, if you're 90% one and 10% the other, you average that based on that weighting of 90 and 10%. When we're talking about isotopes, so for example, carbon-12, and actually this is how we would write them. Typically the mass, you put it up on the a superscript superscript on the left-hand side of the symbol. That means it's the mass. So this is carbon-12, this is carbon-14. Those are both isotopes. They have the same number of protons, but different number of neutrons. And actually, isotopes have the same chemical properties. The number of neutrons don't really affect the chemistry, as we'll get into later on. So we just introduced this idea of grams per mole. At least I said grams per mole, but we really didn't identify the mole. So when we're talking about individual atoms or elements, they're really small. So if we were, we go back to our AMUs and we look at hydrogen, its mass is 1 AMU. That means it's 10 to the minus 24 grams. I don't have a balance that can measure 10 to the minus 24 grams. So if I'm going to measure hydrogen, and typically, put hydrogen on a balance, I need it in macroscopic quantities, right? So large enough where we can actually measure. And so what we're going to do is we're going to go ahead and define a mole as an Avogadro's number of anything. So if I had an Avogadro's number of money, I wouldn't be narrating any of these videos or teaching any of these classes. I'd be enjoying myself because I'd have more money, much more money than anybody else in the world. But Avogadro's number is 6.02 times 10 to the 23rd, right? So it's a very large number. And Avogadro's number is defined such that if you have a mole of carbon-12, so the isotope carbon-12, its mass will be 12 grams. And actually what I should say, it's also based on what we knew before. Its mass is both 12 grams. A mole of carbon-12 has a mass of 12 grams. An atom of carbon-12, or an isotope of carbon-12, has a mass of 12 AMU, okay? Which is nice. It gives us a conversion factor that allows us to use the periodic table. So basically the periodic table, anything that's reported atomic mass for one atom is in AMU, but if we have a mole of it, it's grams per mole. So if we're reading the atomic mass on the periodic table for an element, it can also be related to grams per mole, and that's what we're going to use it most of the time throughout the course. All right, so what we've covered in this video is basically that atoms are composed of these 3 subatomic particles. We talked a little bit about the charges and the properties, like the mass of the particles and the way they relate to the identities of atoms. We defined isotopes, the mole, and then showed how to read each individual box in the periodic table to get information about that particular atom. So until next time.